In this video, I will talk about centripetal force and centripetal acceleration and how these concepts can be applied to different situations. So, centripetal force occurs during a uniform circular motion, and this means that the object is moving in a circle going at a constant speed, and there's always a constant radius. So the motion has to be in an exact circle and not an oval. And the centripetal force pulls the object inwards towards the middle of the circle, and the centripetal force actually makes it continue the circular motion rather than the object just flying out of the orbit due to inertia. And here's another really important point that I had trouble understanding earlier. So the centripetal force is always a net force acting on the object, and it's going to be represented by other forces in different situations. So there's never going to be just the centripetal force by itself. It could be represented by like the force of gravity, normal force, tension, etc., and it could even be multiple forces added together. And also the centripetal force causes centripetal acceleration, which is the object's net acceleration towards the middle of the circle. Because we said the object is moving at a constant speed, but the direction of its velocity can still change. So that's why the object can still be accelerating. And so here you can see that this is the centripetal force, represented by this symbol here, and then this is the centripetal acceleration that's pulling the object into the middle of the circle where it's orbiting. And at any given point, the velocity is going to be perpendicular to the centripetal force. So if there was no centripetal force anymore, then the object would just fly out of the orbit in the direction of whatever velocity it was going at because of inertia. So here are some useful equations to do with centripetal force and centripetal acceleration. And you can write these down if you don't already have them in your class notes, because we're going to do a practice problem later where it's really useful to have these equations for reference. So the centripetal force acting on an object equals the object's mass times its speed squared all over the radius of its circular motion. And remember that the centripetal force is a net force, and we know that F net equals ma. So here we can say that Fc equals mass times the centripetal acceleration. And so here I have some equations for the centripetal acceleration as well. So notice here you can set both of these equations equal because they both equal the centripetal force, and then the masses are going to end up canceling out if you divide by the mass on both sides. So that actually results in this equation here where the centripetal acceleration equals the speed squared divided by the radius. And the centripetal acceleration also equals 4 times pi squared times the radius of the circular motion divided by the period squared. The period represents how long it takes for the object to complete one cycle by going around the circle once. And you might recall that the frequency, which is how many cycles per second, is the reciprocal of the period. So here, if we want to sub in f squared equals 1 over t squared, that's how we end up getting this equation. It's just by recognizing the relationship between the period and the frequency. I would also like to note that the centripetal force and the centripetal acceleration are vectors, so all of these should really be written with little arrows on top of them. I just don't have technology to type that very efficiently, so I've left it out for these equations and for the rest of the video. But if you're writing this on paper, then make sure you include the arrows, so there should be arrows above the centripetal force and above the centripetal acceleration. Okay, so now let's go through some real-life situations where the centripetal force occurs, and we're going to be focusing on identifying what force is acting as the centripetal force. So in this situation, we have an atom where there's an electron that's orbiting the nucleus. So this is the electron that's going around, and then the nucleus is in the middle. And recall that electrons have a negative charge, and the nucleus has a positive charge. So I've drawn that on the picture as well. So if I draw the free body diagram, we only have one force if we're just focusing on the interaction of the nucleus and the electron, and we're ignoring any other forces that could be caused by other surrounding atoms and all that. So the electric force between the two charges represents the centripetal force in this case, because the positive nucleus is going to attract the negative electron. It's trying to pull the electron in towards it. So that's what the centripetal force is in this case. Next, we have a rotating mass on a string. So an example of this would be like a tetherball game. So there's a pole over here, and the ball is on a string, and it's just rotating around here in a circular motion. So in this free body diagram, we have gravity that's pulling the ball down, and we also have a force of tension because of the string. And so if we break the force of tension into its x and y components, here the y component is going to be equal in magnitude to the force of gravity, because it's going to balance that out, and that's what prevents the ball from moving up and down vertically. And then the x component of the force of tension represents the centripetal force, because that's what's going to be pulling the ball in towards the pole. It's going to be what's pulling it over here. And so if this string suddenly broke and there's no more force of tension, then the ball would just continue at whatever its initial velocity was, and it would just go out of the orbit. It would no longer stay in this path because there's no more centripetal force. So here we have an airplane performing a banking turn, and that means it's kind of tilting itself in the air and it's going to end up turning in this direction. So in the free body diagram, we have the force of gravity that's pulling down. But at first I didn't know what other forces are actually here. Like, why does the airplane stay up in the air? Well, this is going to be caused by a normal force of the air acting on the plane. Because the air isn't just empty space. There's actually many molecules and different particles in the air. So the air is able to keep the plane up by causing this normal force that's perpendicular to the airplane. And we can break the normal force into its two components. So this y component is going to balance out the force of gravity, and that's what prevents the airplane from falling down. And then this x component is actually going to be the centripetal force. And since the arrow is pointing in this direction, that's how we know that that's the same direction that the plane is going to turn as it goes in a circle in the air. So next we have a car on a banked curve with friction present. And this is kind of similar to the airplane example in that the car is tilted sideways to allow it to turn. And so you might see this at a racetrack where the car is going really, really fast and it's using this banked curve to help it make the turn. Okay, so it looks like there's a lot of stuff going on in this diagram, but there's actually only three forces. So we have the force of gravity that's pulling down, and here we have the normal force that's perpendicular to the road surface, and we have a force of static friction that's pulling the car down the hill. And the reason why the friction is pulling down rather than pulling up is because we're assuming that the car is going so fast that it's naturally just going to slide up here and off the track. So the friction wants to oppose the car's motion, and that's why it's trying to make the car go down this way to oppose the car's natural motion of wanting to go up. And in this case, it's static friction because we're assuming that the car tires are not sliding against the road surface. So the car is always staying at this exact height on the ramp. It's not moving up or down the ramp in this direction. So now we can break down the normal force and the force of static friction into their x and y components. So again, if we assume that the car is not going to change its height on the ramp, then the net force in the y direction should be 0. So if we have the normal force in the y direction, plus the force of static friction in the y direction, if we add those together, they should cancel out with the force of gravity. And in this case, the x direction is representing the centripetal force, and that's what's going to make the car turn this way as it goes on the banked curve. So there are two forces in the x direction. So we have the x component of the normal force plus the x component of the force of static friction. And so both of those added together are going to equal the centripetal force. So in this case, both the normal force and the force of friction are involved in making the car turn and preventing it from just flying off the turn. So something that I had found difficult about this example when I learned it in grade 12 is how do I know which direction the centripetal force is acting in? Because I made a mistake of thinking the centripetal force is going to be pulling down here parallel to the road, kind of like where the force of static friction would be. But we have to think about the total motion of the car. The centripetal force is always pulling inwards to the middle of the circle of the object's motion. And since we said the car is not sliding up or down here on this ramp, then that means it doesn't make any sense for the centripetal force to be pulling on this same angle here. Because that would suggest that the car is moving downwards, which it's actually not doing. And so that's why the diagram I've drawn here is correct, because it shows the centripetal force is going parallel to the ground level, and it shows the car doesn't move up or down in its height. Today we're just going to do one practice problem together, but you can ask in the comments if you want me to show you a full solution for any one of those examples that we just talked about. So here the question says, a moon with mass 3.0 times 10 to the 20 kilograms orbits a planet, completing one orbit every 16 Earth days. The distance between the center of the moon and the center of the planet is 2.5 times 10 to the 8 meters. Find the magnitude of the gravitational force between the two objects. So a really good first step is to draw a system diagram, and this lets us visualize what's happening here. So this is the planet, and then this is the moon orbiting around it, and we're assuming that this orbit is perfectly circular. And I've labeled the radius, which is the distance between the center of the moon to the center of the circle that it orbits. And notice that the radius is specifically between the center of both of these, and I've said that in the original question. And that's really important because the equations won't be accurate if you only did the distance reaching like the edge of the two objects. It has to be from the center to the center. And so this is the free body diagram for forces acting on the moon. So there's only one force, assuming that there aren't any other planets in the surroundings that are causing forces on it. We're just focusing on these two over here. So there's the force of gravity that's pulling the moon towards the planet in the center, and in that case that's the centripetal force because that's what's keeping it in the orbit. So now let's make sure that everything in the question is in the correct units, because in physics we use meters, seconds, and kilograms. So the mass is in kilograms, so that looks good, and then here the distance is in meters, so that's fine as well. But here we have a problem. It says 16 Earth days. We don't want days, we want seconds. So we have to do a unit conversion. So since it says Earth days here, that means we can use normal conversion factors where 1 day is 24 hours. So if we set up the ratios here, we have days and hours, hours and minutes and seconds. So notice that the days are going to cancel, the hours will cancel, and the minutes will cancel. So our final units are seconds, which is exactly what we want here. So I put this into my calculator and I got 1,382,400 seconds. So that's the same thing as 16 days. And so that represents, this is how long it takes for the moon to complete one orbit of this circle. So now let's think about what does this information from the question represent in terms of variables in our equations. So the moon's mass is 3.0 times 10 to the 20 kilograms, and we know that the radius is 2.5 times 10 to the 8 meters. And so this value we calculated here is actually representing the period, because the period is how long does it take to do one cycle. And so our goal here is to figure out what is the magnitude of the gravitational force between these two objects. So now we can use some equations to solve it. So the first thing we need to recognize is that the gravitational force is the centripetal force in this situation. So we can use all the equations that we had looked at about centripetal force. So remember, the centripetal force equals the object's mass times the centripetal acceleration. So we can just plug in the gravitational force there for the centripetal force. And we know the centripetal acceleration is 4 times pi squared times the radius divided by the period squared. So if we sub this in here for the centripetal acceleration, then this is the new equation that we get. And so if we look at the given information, we can plug it in because we know the mass, we know the radius, we know the period, and there should be a pi button on your calculator, and if there isn't, you can just say like 3.14, like you can approximate it. So we know everything in here. So if we sub in our numbers and you put that into your calculator, then you should get that the force of gravity is about 1.5494 times 10 to the 18 newtons. But in the question, we only have two significant figures. So then this will round to about 1.5 times 10 to the 18 newtons. So this represents the force of gravity acting on the moon caused by this planet. Okay, so that's all for today. Thank you very much for watching, and let me know if you have any questions, and I'll do my best to answer.